Okay, let's start.
We're going to continue with 2.3 and 2.4. Yeah, I know you guys are upset with me, but I don't have your test today. I really tried to get them done by today, but it didn't work out.
You can cover a quiz.
Huh?
Make it up to us by covering a quiz.
By giving a quiz?
Curving.
Curving that quiz?
Yeah.
It was bad?
Yeah.
Just drop it.
Just drop it.
Yeah.
We didn't know.
I have no idea, but it's been a long time and a long
It's been
midterm season.
a long weekend.
A long midterm season. Let's look at, like, half of us probably left at least one question.
Can we do something where we like
I don't know.
do
Let's
corrections?
let's look at it because
No,
let's.
then I'll make it worse.
We're actually going to do some similar problems today and then move on, but let's actually look at it. So,
Bonus question.
well, the bonus questions are bonus questions, and these are from like actually chapter 3. So the bonus questions are.
When you like don't get any of them. Yeah.
But yeah, so the problem 1 was to define the derivative.
We need to find one. It's f of x minus h. F of x plus h minus.
The limit as h approaches 0
Limit as h approaches 0
of f of x plus h.
of that stuff. Right, so that's the difference quotient. And that's the.
I didn't find the limit.
Okay, so in part 2, you're given a function. And it says find the derivative by doing the following. So I'm going through the steps of computing the derivative using that formula. So in part A, all you had to do was plug this formula into that expression. Don't simplify, don't do anything. Just plug this into that and write the answer down. Okay, so that would have given you. You're just going to replace all the x's with x plus h. Minus parentheses, replace, just copy the function. And put it all over h, and that's, you just leave it. And that would have been part A and 2. Now in part B, I asked you to simplify it to the point just before you plug in that h equals 0. So you're just going to start to distribute here. So that was the answer for part A, for you to just write down that expression. And this part now we're just going to simplify, so we're going to expand the brackets, parentheses. So it's 2 minus x minus h minus x squared minus 2xh minus 2 plus x squared all over h. The 2's would die, the x's would die, the x squares would die. And there will be a common h in all the terms left over, so you have to factor that out. And I left over with the minus h. So that would cancel. And so basically this is what you would write out. So then you write that in part B. And so your final answer now is when you plug in h equals 0, so in part C.
The limit as h approaches 0 for it to be right? For that one.
Because I forgot to write the limit wrong.
Could we just write the stuff in parentheses and have it be right?
Please.
Just drop it.
I'll accept it this time around, but you really should be writing a limit.
We got it.
So the final answer is just now you actually take the limit by plugging in h equals 0. And so that would just be minus 1 minus 2x would be the answer to part C.
I did that.
Yes. Change my answer.
And then in problem 3, it says we wanted to find the equation of the tangent line to this curve at the point 0, 2. So in problem 3, we want the tangent line
Bro, I literally
to
could
f of x at 0, 2. So basically what we're going to do is, remember the tangent line is just a straight line. The difference is the slope comes from the derivative at the point. That's what makes it a tangent line. And so basically here, notice here that my x is 0. So this would mean my slope is the derivative evaluated at 0. So I'm going to plug 0 into this expression, and the answer is going to be -1. So that is my slope. And I know the point is 0, 2. So now I would just use y minus y1 equals mx minus x1. And so that's y minus 2 is equal to m, which is -1, x minus 0. And that would be the answer.
Can you like it?
Can we go over the bonus ones so I can maybe feel better about myself?
You think you know them?
I think I got one of them. I mean, I hedged my bets and I used a couple different strategies, so maybe I got one right. As you can see, there's addition.
So the bonus problem was for you to come up with some shortcut formulas. So one was if you have one function times another, how do you differentiate that? So this is f of x and g of x.
Is it addition?
This was a multiplication.
Yeah. What is the derivative?
This means take the derivative of. This is take the derivative of one function times another function. Yeah?
You take the derivative of f of x and multiply it by the derivative of g of x.
No.
No. Is it addition?
Isn't it f of x times g prime of x plus g of x times
I
times g?
know.
Yeah, this is something called the product rule. You differentiate one of the functions, you leave the other, plus you leave the first, you differentiate the second. So it's something we'll talk about in chapter 3. To actually apply that limit to a multiplication, it doesn't just multiply each term. There's going to be I'll actually prove this for you. You'll see why if you're multiplying two functions, taking their derivative means you have to do this.
I don't remember shit from 2 years ago.
There's another one, we'll say, how do you take the derivative of a division of functions? So if I had one function divided by another, how do I
Same
divide the
thing, but with
derivative?
it
It's not you divide, you just differentiate each. Yeah?
You do g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x.
Yeah. What if you had to differentiate a composite function, f, and the function inside g of x? Yeah?
You take the derivative of like f of g of x, like maintaining g of x, and then
So you take the derivative of the outside function, leave the inside function alone.
yeah, and you multiply it by the derivative of the inside.
Then you multiply by the derivative of the inside. These are 3 very important rules. This one is called the product rule, that's called the quotient rule, this is called the chain rule. And then there's this one, which is called the power rule. How do you differentiate something that looks like that, x to a constant? Yeah?
You bring the x down, the n down in front of the x, and then it's n times x to the n minus 1.
Raised to the n minus 1. Yeah?
Okay, I have 2 questions.
So we haven't done this yet, but we will prove it
I
pretty
think
soon
the second
in a
one
couple
depends on the
classes.
answer to the first. Is
The
it possible?
second one,
The second question I'm gonna ask depends on the answer to the first.
okay.
Is it possible that you drop a quiz if the average is like nothing? Is that like, does that happen?
I dropped 2 quizzes automatically.
Oh, you do.
Oh.
Thank God.
Okay.
And not counting the diagnostic. The diagnostic quiz doesn't count as a
Yeah, no,
quiz,
that's-
but of all the other quizzes, two are going to be dropped.
Okay, and then my second question, is it possible, like in any way, shape, or form, to either do corrections or do an assignment to like make up for any lost points on quizzes?
Do well on the test is how you make up the
Okay.
points. Yeah.
Okay.
So, that being said, a problem like on the quiz is definitely going to be on the next test. I'm definitely going to have a problem that says, here's a function, use the limit definition to find the derivative, and use that to find the tangent. There's definitely going to be a problem like that. So if this quiz really knocked you down, you can make up for it by doing well on the next test. Yes.
First one, what's the difference between working the prime?
Wait, can't hear you. What?
Like, put the prime thing next to the F.
Yeah, the prime means take the derivative of the f and multiply it by the g, and then you add it to leave the f alone and multiply the derivative of the g.
Unless you do it to the F and 2.
Yeah, you multiply one at a time and you add them together. That's called a product. We haven't done this yet. This is chapter 3 when we start to learn all these nice formulas. So we will actually do it. Yeah, a quiz every week is the how you want to think about it. So it's not the Tuesday that's important. It's always being on your toes is what's important.
So is the quiz next week gonna be on Tuesday, Friday?
Tuesday. Like the first time I see you during the week, there's going to be some sort of assessment of what you understand versus what you
So
understand.
the next quiz will be on wherever we finish today.
Yes. So we're going to do a lot more. We're going to do, well, a few more examples of the kinds of things that is on that quiz. And then I'm going to really talk about some conceptual things, some concepts that are really important for us moving forward. So let's actually do that. So we actually found the derivative of x squared last time using the limit definition, and we actually found the equation of the tangent line to y equals x squared at x equals 2. Let's actually do that a few more times because this is actually an important process to learn. So use the definition of the derivative. Find f prime for the following. So one was f of x equals x squared. We actually did that last time. So that's done. The second example I wanted you guys to look at is, what about a constant? So see, here's a constant. How do you find the derivative of constant? What if it was just the derivative of x? What if it was just the derivative of square root of x? I also asked about 1 over x. So we're going to figure out the derivatives of all these functions using the definition. So A was done last time, so let's start with B. So here we know that our f of x equals c, so our f prime of x, especially if you don't remember the formula, I would suggest that you write it down every time you're going to use it. Just the repetition will help you remember it. It's going to be limit as h approaches 0, f of x plus h minus f of x over h. Just the limit as h approaches 0. What is f of x plus h if my function is a constant? It's just c, right? There is no x to plug into. It's a constant function. The output is always c, no matter what the x value is. So it's c minus f of x, which is also c. So that's just the limit of 0 over h, which is just 0. And by the way, this at this point you can think of this as a general rule if you want. The derivative of a constant is always 0. So if I ask you, what is the derivative of 5? It's 0. What is the derivative of pi? It's 0. What is the derivative of e? It's 0. What is the derivative of 2.79? It's 0. Derivative of a constant is always 0. One way you can remember that is that a constant, y equals a constant, is just a horizontal line. What's the slope of a horizontal line? 0. Remember, derivative is just the way to get to the slope. Okay, so derivative of any constant is 0. That's something you can know now. Derivative of a constant is 0. Right, we will be getting to some shortcuts to find derivatives of certain functions later on, but for now we're using the definition over. What if it's actually just the function x? So what is f of x plus h when the function is x? X plus h. We replace all x's with x plus h. So I replace that x with x plus h. Minus f of x, it's just x, all over h. Those x's would die, so I pretty much end up with a limit as h approaches 0 of h over h. That simplifies to 1, so that's just the number 1. So in other words, you can take that as a rule. The derivative of x is 1. There's going to be a general rule that will cover both these cases, but it's nice enough. These are nice enough and common enough to just know them automatically. Right. The power rule that I mentioned earlier, the fact that the derivative of x to the n is n x to the n minus 1, you can use that rule and derive both of these. But derivative of x is 1 is kind of something you can just know right away. Another very common function that we find the derivative of all the time, which you probably don't want to have to use a rule to figure it out, is the square root of x. You'll see it all the time. So it's kind of nice to just know a formula for it. So let's say our function is radical x. I want to find the derivative of radical x. What function will give me the slope at any point for radical x? So what is f of x plus h here? This is f of x plus h minus f of x over h. What is f of x plus h if my function is radical x?
Square root of x plus h.
Minus the square root of x all over h. How do you simplify something like that?
Conjugate.
Conjugate. Top of it. So you multiply by the conjugate, that's how you'd simplify something with two terms and you have a radical. So now the top becomes like a minus b times a plus b, that's the difference of squares, so I'm just going to square this minus the square of that. So the top just becomes x plus h minus x. The bottom would become that. My x's would die, my h's would cancel. So I pretty much have 1 over the radical of x plus h plus radical of x. At this point I can plug in h equals 0. And so I have 1 over radical x plus radical x, or in other words 1 over 2 radical x. And that's just something you can know now. The derivative of radical x is 1 over 2 radical x. Also something you can derive by the power rule, but it's nice to know it without having to go through that. So my next example was 1 over x, but I actually want to use that in a bigger example, so we'll deal with it there. Okay, so here's a big example. It's pretty much the question that was on your quiz, but here's how it would be phrased. So full disclosure, nothing up my sleeves here. There will be a problem like this on the next test, definitely. Worded pretty much exactly the same way. The only difference is going to be the functions that are involved and the point that I'm asking you to do that. But it is something that, if you go through a Calculus 1 class, it is a kind of method or a technique that people expect you to know how to do. Compute a derivative using the limit definition and use it to find the equation of a tangent line. So, So it says use the limit definition or the definition of the derivative. Find f prime of x at x equals 1 if your f of x is this function, 0 over 1 is this. And then there's going to be a part b, hence find the equation of the tangent line to f of x at the point where x equals 1. So there'll definitely be a problem like this. It'll be one problem with two parts, just as how there was a problem on the last test where I asked you in part A, just tell me what the difference quotient is, in part B, find the difference quotient, and it was just like one big problem like that. A problem like this will be on the next test. It's a very important thing to be able to do. And of course, if the problem says use the limit definition of the derivative, if you use any other method, you won't get credit for it. I'm specifically testing your ability to use the definition. Right, so while by the time the second test comes around, we will know shortcuts. We will be able to differentiate this without using the limit definition. But here I'm specifically requiring it. And then I want you to use that answer to find the equation of a tangent line at a certain point. So you can redeem yourself for the quiz by doing well on this problem on the test. And when I grade the test, I do keep a tally of how many points each student gets per question. So that I can look, oh, this person, they did bad on quiz 5, but on problem 1 in test 2, they did great. So I see improvement here. So let's actually do this. Part A, our f prime using the limit definition is f of x plus h minus f of x over h. So we're going to start to plug in here. So here's my f of x. What would my f of x plus h look like?
3 minus 1 over x plus h.
Right, I'm just going to replace that x with x plus h. So it's 3 minus 1 over x plus h minus the original function, parentheses, all over h. Now at this point the 3's will actually kill each other right away. So 3 minus 3, that goes away. And then I have minus a minus 1 over x, that gives me plus 1 over x. So this just becomes limit is approaches 0 of this plus that. How do you simplify something like that?
Do you get the denominators on top first the same?
So you get the LCD, and the easiest way to simplify that is to multiply and divide by the LCD. So that's the product of the denominators on the top. This of course distributes. So in the first case, the x plus h's cancel, I'm just left with a minus x. Plus in the second case, the x's cancel, I'm left with an x plus h. All over h times x plus h. Minus x plus x goes away, then my h is going to cancel the h here. And so ultimately, I would end up with 1 over x times x plus h. At this point, I can plug in h equals 0 and not divide by 0. So I just get x times x, or 1 over x squared. This means, don't forget the question. This happened to some of you on the test. Didn't finish grading it, but I started grading it, and I'm seeing some mistakes. Here, if people forget in parentheses was a problem sometimes. People not answering the question. So here, I didn't just ask you to find f prime. I asked you to find it at x equals 1. So you're not done here. Once you get here, that's f prime in general. That's f prime of x. So now I want you to find it when x equals 1. So the answer you should have here is f prime of 1 is going to be, now you plug in 1 into here. So f prime of 1 is 1. And that's your answer to part A. Any questions on that? Yeah.
I'm sorry, I'm still like a little confused where you multiply by the denominator thing over there.
This is the LCD. This is what we call a complex fraction. And the easiest way to simplify that is to multiply and divide by the LCD. And so how you multiply fractions is you multiply the tops and then you multiply the bottoms. So in the denominator, I just multiply straight across. I get hx, x plus h. In the top, there are two terms here, so I distribute it. So I multiply this by that. And so the x plus h's would cancel. And then I'm left with the x. And when I multiply this by that, the x's cancel. And I'm left with the x plus h. And at that point, I would have minus x plus h over hx, x plus h. These died, and so I would end up with h over hx times x plus h. H's would cancel because now there's only multiplication, so I end up with 1 over x times x plus h. And then it asks me to find the derivative at x equals 1, so in that formula I will plug in x equals 1, and so that's the answer to part A. Now the part B asks us to hence find the equation of the tangent line to that function. So now, just remember, tangent line is a straight line. So we need n and a point, right? If we have the slope and a point of a line, we can find the equation of a line. We can also find the equation of a line from 2 points, but we only have 1 point here. We only know the point where x equals 1. We don't have another point. So we need the slope. Now the slope in a tangent line, remember, comes from the derivative evaluated at a point. Right? That's how you get the slope of a tangent line. So in this case here, my n is going to be 1 from part A. Because the slope up to my tangent line is the derivative at the point, which I found in the last part. So that's the first thing that we need to know. The second thing that we need to know is the point. Now for the point, I know my x value is 1. So I need to find my y value. How do I find the y value? Yeah?
You plug the x equals 1 back into the original.
Back into the original function.
Yeah.
So y will be, I know it's 3 minus 1 over x, so it's 3 minus this over 1, and that would give us 2. And so I know now that the point is 1, 2. And at this point, that's easy, but you really want to get that through your heads very solidly, that when you want to find a coordinate, you use the original function. We're going to be using several derivatives at a time, and we're going to be finding different things, and you need to know what to plug into which function. If you're finding a coordinate, you should be plugging into the original function. If you're finding a slope, you should be plugging into the derivative. And these are things that you need to know. And there are going to be other things that you're going to want to find that you want to plug into the second derivative, which we'll talk about today. But yes, to find the coordinate, we plug into the original function. That gives us the y-coordinate. So now we have the slope and the coordinate. We can find the equation of the line. I would use y minus y1 equals mx minus x1 and just plug that in. So it's y minus 2 equals 1 x minus 1. And so that's the equation of your tangent. I never asked for it in specific form, so I never said you had to go to the slope-intercept form, so you don't have to do it. That would be acceptable. You could take the extra step and write it in x minus 1 plus 2, and that's also acceptable, but really, I don't.
Wait, you were given the coordinates, right?
We were told that x equals 1.
Okay.
So to find that coordinate, I had to use the given function. So the given function is what tells me the outputs. It tells me the y value. So if I know an x value, I can find the y values by looking at the original. If I need to find the slope at a certain point, I look at the derivative. If I need to find the y coordinate at a certain point, I look at the original. And so that would be the problem. So there will be a problem very similar to that on the next test. It's a very standard procedure. Standard kind of thing to ask. Are there any other questions? So we're going to move on to some very important ideas here. So it's not going to be too much computational examples. They're just some ideas that I want you to get used to so that when we're doing the computation, you have some sort of context for them. I want to talk about the notion of a second derivative. So there are a few things here to clarify. No. We can take derivatives several times with some functions. Most functions, well, every function in this class that we will be dealing with are very nice functions. You'll actually be able to take the derivatives forever. So you can take a derivative and you get an answer, you can take a derivative of that, get an answer, take a derivative of that, get an answer. You can do that forever. Not all functions are this nice, but some of them are. Those are going to be the ones that we're going to care about, at least the ones where we can do this process twice. That's where we're going to come up with the second derivative. So if we take a derivative and then take the derivative of the result, this new result is called the second derivative. Of course, in theory, it might be possible to do this again, and we can find a third derivative, and a fourth derivative, and a fifth derivative. But we won't be using the applications of any of those in this class. We will be using applications of the second derivative. If you're in a class where you're using applications of the third derivative, it's a serious math class. It's not going to be Calc 1. Right, but there are uses to higher derivatives, but for now we only actually care up to the second derivative. So the notation for this, you do have a prime notation, so it's f double prime. You put 2 notches instead of 1. That just says I took a derivative and then I took the derivative again. In terms of the Leibniz notation, it's d squared y dx squared. Right, because basically what happens is you took the derivative of y with respect to x, and then you took the derivative with respect to x again. So you get d squared over dx squared times y. So again, I'll mostly be using this notation because it's easier to write down. If you see either one in your homework, you should understand what it means. So it just means the second derivative. This means you took the derivative, and then you took the derivative of the derivative. And so that gives you a second derivative. And the second derivative as many applications. Let's give you one basic application. Are any of you taking physics? Or have to take physics at some point? So basically, you go to a general physics class. In chapter 1, it's going to be about motion. And the second derivative actually applies to motion. So one application is the physics, and it's the physics of motion. So for example, if you have, S is the standard variable used, I'm not exactly sure why, actually. But if you have a function that gives you the position of an object at time t, then you can take the derivative of this function, perhaps, and that will give you the velocity of the object, the speed of the object in a certain direction. Right? That's the first derivative. It gives you the rate of change, the speed. Now it turns out that sometimes you can take a derivative again, and I can take what's called the second derivative of the position. And what that gives me, this guy is usually denoted v of t. In the physics class, you would call that v. And this guy is what will give us acceleration. That's usually denoted by lowercase a. So there will be three main symbols in motion when you're doing physics. There will be S, there will be V, there will be A. This represents your position, that represents your velocity, which is how fast you're moving in a certain direction. This will represent your acceleration. Acceleration is very important because something like gravity, for example, is an acceleration. When you talk about the force of gravity, you're talking about an acceleration. Going back to what we know about derivatives, what they mean. Remember, a derivative of a function just tells us about the rate of change of the function. So the derivative of S is telling me how fast is S changing, right? The rate of change of position is velocity. So in that interpretation, the rate of change of velocity is acceleration. So if I want to know how fast is the speed itself changing, that gives me acceleration. So when someone says something like gravity is minus 9.81 meters per second squared, they're not telling you a speed of gravity. There's no speed of gravity. But that is how gravity would speed something up, right? So if something is moving at a certain speed and falling to the ground, if you forget about air resistance and all that, gravity will increase its speed by that much every second, right? So that's how you can think about acceleration. It's how fast your speed is changing, and it turns out it's actually the second derivative of something. So there's an application of physics. There's a geometrical application to it as well, and this is where we'll spend most of our time. There's something called concavity. I'm going to talk about what that means. So this is another application of the second derivative. So let me give you a definition here. F of x is said to be concave up. So I'm telling you about one of the versions of concavity. There's such a thing as being concave up. On an interval, if it always lies above its tangent line on that interval. What does that mean? Basically means that the graph is going to be shaped like this. Notice that in this graph, with this shape, if I put a point and draw a tangent line to it, the graph itself is always above the tangent line. Whenever a graph has that kind of shape, we call it concave up. There's actually a mnemonic for that, which we'll be using all the time pretty soon. You say concave up like a cup. So concave up like a cup. You're up, you're a smiley face, this is your shape. And the shape is going to be important. The shape can have an interpretation on it. right? So you say you're concave up like a cup, right? Now how does this apply to the second derivative? Well, look at your tangent lines. What is happening to your tangent line? They're getting steeper and steeper and steeper if I keep drawing them along this curve. So if I'm measuring how the tangent line is changing as I move along this curve, the slope is actually increasing. But how do we measure when something is increasing? Well, we take its slope. So to say the slope is increasing, what we do is we would take the slope of the slope, and that's how we can describe increasing. And we also spoke about how to talk about increasing based on a slope. It's when a slope is positive. And so that basically means a graph will have this shape if the slope of its slope is positive. And so that gives us the following. So note the slope of the tangent lines are increasing. This means the slope of the slopes is positive. Right, we spoke last time about straight lines, and when you have a positive slope, you're moving up as you go from left to right, and so that's a characterization of being increasing. And so this basically means your second derivative for your function will be positive if and only if it has this behavior. So this means, this is one way we can characterize being concave up. Right? So you're concave up like a cup, you're happy, you're smiling, you're feeling positive, you know, everything is nice. This is called concave up. Okay, so this is one behavior that a graph can have, and it's going to be a behavior that's actually going to be meaningful to us. So I can give you an example. What does this mean? There are several situations that you can get from this. If you see something like this, let's say there's one situation where you might see like a cup that looks like this. And why something like that might be important to you is because you might want to be able to locate the lowest point here, right? That's you locating the minimum of some value, right? So one way you can do that is to figure out where things are concave up, and then figure out when is the lowest dipping point of that behavior, and that's actually a way to locate a minimum point. You can actually locate minimums based on second derivatives, and we'll talk about that later on. You might have remembered that we can do this for parabolas pretty easily. That's just finding the vertex. There's a nice formula for it, minus b over 2a. It turns out for general functions there is no formula, right? So being able to find the minimum point of some general random function, there's no formula for it. What you'd use is derivatives. That's how you're going to find minimums. So if you ever want to minimize something, you can actually search for all the areas where it's concave up. It's one of the ways to do it. We'll talk about others, and identify minimums. Here's another situation. What if it's not like a cup that can hold water, but it's actually like slanted like that? What does that behavior represent? Well, notice what this means here is the function is increasing. Because it's moving up as I go from left to right. But it is doing so faster and faster. This means if you see a graph having that shape, having that behavior, what it means is, sure, it's increasing, but it's actually increasing by more and more and more. So one interpretation of this, there are many, there's an infinite number, it depends on what this function is measuring. But let's say I'm tracking my weekly sales in a store that I own every week. And I realize that after tracking all these points, I'm plotting a curve that looks like this. What would that mean for my sales? Well, that would mean business is very good, right? Because that would mean not only are my sales increasing, but they're increasing by more and more every week. So my sales might have increased by 10 products sold in the first week, then they increased by 30 products sold in the next week, then they increased by 50 products sold in the next week. Like I keep selling more products, and the amount I'm selling more of, that itself is also getting bigger. So in terms of sales, that would be great, right? If this function is tracking the number of cancer cells in my lungs, that would be very bad. That means that the cancer is increasing, it's getting bigger, and it's getting bigger faster. So the damage that the cancer was doing to me last month is actually a lot less than how much damage it's going to do to me this month. And I can figure that out by looking at a graph and realizing that it's bulging in this way, right? So there's an interpretation you can put on this, right? So concave up means in the event that you're increasing, you're doing so faster and faster and faster. In the event that you're decreasing though, it actually means you're doing so slower and slower and slower. So I could be concave up and decreasing. Right? These are all concave up like a cup. They all have that shape. My second derivative will be positive in all these instances. But this characterizes a function is decreasing, but decreasing by less and less over time. So if that function represented my sales quota per week, business is bad, but there seems to be hope. It seems to be getting less bad as time goes on. Sure, I couldn't sell 10 products last week, but I only couldn't sell 5 products this week. So something is getting better. It's still bad. I still have unsold products, but the situation itself is actually not, it's getting better as time goes on. And so a graph would, how you would interpret that from a graph if you're tracking it is this particular kind of shape. You would be concave up and you would be decreasing. Of course, the phrase concave up is very suggestive. You might ask, is there a concave down? And yes, there is. We could actually move the opposite way here. So let's talk about that and some interpretations that we can put on that idea. So f of x is concave down on an interval if it lies below its tangent lines. In that interval. So that is talking about this kind of behavior. Right? So if I were plot points and were to draw tangent lines, my graph is always below the tangent line. You might notice that the slopes in this case are actually decreasing, which means the slope of the slopes will be negative. Right? And so that gives us when the second derivative is negative, is when you are exhibiting this behavior. So there's also a mnemonic for this. Concave down like a frown. Down like a frown. It also means that your second derivative is negative, right? So you're concave down like a frown, you're negative, you're down, you're sad. Okay, so that's how you remember that the second derivative, because the sign of second derivative is the important thing here. You need to somehow create a connection in your mind of what signs you should be looking for when you're looking for a certain kind of behavior. So concave down means down like a frown. Mathematically what that means, the second derivative is negative. You're down, you're feeling negative, you're frowning, you're sad. What does this mean? So let's just talk about some of the applications. So one, this can help us identify maximums. So you can think of a parabola that's inverted and the vertex is the top guy. I can actually use the second derivative to determine when a maximum is going to happen, right? And again, do not underestimate the power of that, because you might be thinking of, you might see that and you think quadratic, but we won't always be dealing with quadratics. in general, there is no formula for vertices. You do not have a general formula for the vertex of a random curve. You use calculus when you want to compute it. Right? So you can use this to help you find maximums. You can also be doing something like this. Right? So this means function is increasing. But doing so less and less over time. Right? So to go back to the sales example, let's say I'm plotting my weekly sales, and that's what the curve looks like. What that would tell me is that business is good. I'm selling more every week, but the amount by which I'm selling more is actually decreasing. So this would kind of suggest to me that things are good now, but they're probably going to get bad pretty soon. You kind of see what I'm saying? So it tells us that it's not just a matter of, oh, are we moving up or down? It's how we're moving up and down and what that can mean in the future, what predictions we can make. If this pattern continues, pretty soon what's going to happen? Right? You can kind of see, well, you know, right now we're good, but on the horizon something might be going on, and so we'll probably need to worry about that. You could also have the third situation where you're doing this, right? And that just means you're decreasing, but doing so more rapidly. So if this pattern continues, it can actually turn into a situation where you get exactly the opposite of what you want. And so identifying such patterns can be important. There's an important idea that can come out of this, and that is the idea of a so-called inflection point. Does anyone know what an inflection point is?
It's when it switches direction between like convex and concave.
Concave up and concave down. Yes, it's when the concavity switches on you. An inflection point is a point where concavity switches. Right? So this is if your graph looks like this. That point here is the inflection point. You'll notice that if I'm to the left of this point, I'm concave down like a frown. I'm shaped like a smiley face when I'm over here. But once I pass that point, now I'm shaped like a cup, like a smiley face. I'm positive, I'm happy, and that's concave up. So at this point here, I switch from a situation where I'm concave down, and I switch to a situation where I'm concave up, right? So if this is my sales quota every week, I'm like, yeah, business is good, but I kind of feel like something's gonna happen. Okay, let's do something. And then this starts to happen. We must have done something right. You know, whatever we did on that week, we should do more of that. Because that's making our business better, and it's making it better by more every week. That's the kind of situation you want to happen, right? Or you can do something like this, right? So that's probably, yeah, sales are good, we did something, sales are still good, but it's probably just the momentum of it being good before. Obviously now things are starting to kind of slow down. Whatever happened that week, we should probably do less of that. You know, so you can look at a graph and you can kind of see when something changes, and based on what that graph is representing, you can interpret that into actions you might want to take, actions you might want to avoid, whether you want to try something new, try something different, double down on what you're already doing. Right, so the shapes of your graphs, they can mean a lot. But actually characterizing a random graph of some random function that you're making up by taking statistics every week is difficult, and calculus is what comes to the rescue, because there is no formula, no general formula here. So we really look at derivatives to talk about these kinds of behaviors. So we can also be doing that. right? Or we can also be doing that. You know, these points here, where we actually switch from one concavity to the other, these are called inflection points. Okay. So this is representing the number of cancer cells in my lungs. Okay, so whatever the doctors are doing seemed to be working, but whatever we did this week, now it's less effective. It's still working, but I kind of feel like progress is slowing down. You know, there are interpretations you can put on. So that's kind of how you can use a second derivative to talk about certain behaviors of functions and what that might mean and what an inflection point might mean. It of course all depends on what this curve is actually representing. But that it will give you some ideas on what you want to identify, actions you might want to take or not. So I do want to talk about that, but that's probably going to take too long. We ended now. Never mind. So I'll see you guys on Tuesday. We'll have your test due on Tuesday, and we will have the solutions for the tests are already online by the way, but I didn't finish grading. So you can look at that and judge how well you did, but I will see you guys on Tuesday. Not due yet.
Oh, so you said it was 2.2.
Oh, that's the limit.
Yeah.
Okay. So we don't have homework due for next week, but the limit homework is due this week, 2.2.